Module 7, and the previous module we talked a little bit about different circulations, and then we really got into global scale circulations. Well, this particular module, we're going to be talking a lot about synoptic scale circulations and synoptic scale weather events, particularly the ones that affect us the most, which are mid-latitude storms. And mid-latitude storms actually have pretty major implications on the kind of weather we get here, even here in California, but across the United States as well. Whether it's a tornado outbreak, or a nor'easter, or a major blizzard, or a major rain event, like the ones that we get here in the wintertime, almost all of those phenomena are associated in one way or another with a mid-latitude storm. And so that's really what we're going to be focusing on in this module. The goals for this module are first to understand what an air mass is and the key properties of an air mass, being able to use those properties to determine the source region of an air mass and to be able to identify the air mass based on its source region. Then we're going to talk a little bit about fronts, how fronts work, and explain the conditions before, during, and after a frontal passage. And that's what this week's activity is going to focus on. And then finally, we're going to talk about what's called cyclogenesis, and really the life stage of a cyclone. So, a lot of interesting things to talk about this module, so let's jump in. This is lecture 24, which is on air masses, and it's based on pages 224 to 234 in the textbook. That might vary a little bit depending on the edition you have, but that's what this first lecture is going to be based off of. So first, let's talk about what an air mass is. An air mass is a large body of air. And when I say large, I mean hundreds, if not thousands of kilometers in width. And inside this air mass, you have air that has pretty similar characteristics throughout. Similar temperature, similar humidity, similar moisture content, and so on. And these air masses are constantly moving. And by constantly moving, they're bumping into one another. They're pushing each other out, they're undercutting one another, and so on. And the boundary between any two air masses is what's called a front. Now we're going to talk more about fronts in the next lecture. But for now, let's talk a little bit more about these air masses. So, what determines the type of an air mass we have is the air mass's source region. Now, a source region is a region that is large, it's homogeneous in composition, meaning it's uniform pretty much all throughout its area, and it's what determines the air mass's conditions, the air mass's characteristics. Now, if this were a lecture class, I would be asking you to give me an example of a source region, but I'll just name a few here. Oceans are excellent source regions because they're vast, they're homogeneous in composition in that it's pretty much ocean all the way out, no big changes in elevation, obviously. And they don't really change much over a large area. You have to really go either very, very north or very south to experience a substantial change in ocean composition. So that's usually a pretty good source region. Another good source region could be a wide desert area. So an area that could be hundreds or even thousands of kilometers in width, very flat. Plains, such as the Great Plains, could potentially be a good source region, though I'll talk a little bit about why the Great Plains, maybe not so much. But, so those are just a few examples of source regions. So the ocean's a good source region, plains are a good source region, deserts are a good source region. And each one of these regions imparts its characteristics, imparts what it's about into the air mass. For example, just going back real quick, if the air mass forms over the ocean, it's going to be a pretty moist air mass. If the air mass forms over the desert, it's going to be a very dry air mass, and so on. So let's talk a little bit about each of these source regions. First, let's talk about the latitudes of these source regions. Now, the latitudes determine whether the air mass is going to be a warm air mass or a cold air mass. And there are three main latitudes that we're interested in. The first that we're interested in is what's called the tropical latitudes. These form warm air masses, and these come particularly south of 30 degrees north or north of 30 degrees south, so closer to the equator. And these are warm air masses. Then there's polar air masses. Polar air masses are cold air masses, and they come from north of 50 degrees north or south of 50 degrees south. So they're much closer to the poles. And as a result, the air that forms there is much colder. And then finally, there are what are called Arctic air masses, and these are air masses that originate pretty much right over the poles. These are very deep polar air masses. They're extremely cold, much colder than even regular polar air masses. And so these are the three latitudes we look at: tropical, polar, and Arctic. Tropical are warm, polar are cold, Arctic are very cold. Now the next thing we're going to look at is the composition of each of the source regions. There are two types of compositions that we're going to talk about: maritime and continental. Maritime air masses are air masses that form over the ocean, and they're moist. Why? Because they have lots of water beneath them. On the other hand, continental air masses are dry air masses, and they form from inland locations. Now that we have that down, we actually classify an air mass based on those previous two characteristics: its latitude and its composition. Those two things tell us everything we need to know about an air mass. And using those two things, we can put together a matrix very similar to a Punnett square if you've ever taken biology, and we can use them to classify 5 different air masses. The first 2 air masses are called tropical air masses. These form in the tropical latitudes, and they're warm. If a tropical air mass forms over the ocean, it's called a maritime tropical air mass. These are warm, moist, and usually unstable, and this is because there's a lot of heat and a lot of moisture available there. And so you get a lot of thunderstorm formation along maritime tropical air masses. On the other hand, continental tropical air masses, these form over the tropical regions but over land. These are hot and dry air masses, and these are unstable near the surface, but usually much more stable higher up. And that's because the most of the heat is located near the ground, but because heat rises, the air aloft doesn't cool rapidly. And then finally, well, not quite finally yet, but then the next category we look at are called polar air masses. If a polar air mass forms over the ocean, it's called a maritime polar air mass, cool and moist. If it forms over land, it's a continental polar air mass, cold and dry. And then finally, if it forms in the Arctic regions, very cold. And there's only one type of Arctic air mass, and it's called the continental Arctic air mass. And it's extremely cold, extremely dry air. Now, before I continue on, I do want to quickly talk about the language that I'm using here. I mentioned warm, hot, cool, cold, maritime, continental, and so on. But let me briefly explain why I'm using warm and hot and what the difference between the two of them are, cool and cold and what the difference between the two of them are. And maybe that'll also help you understand while Arctic air masses only form over land. So, oceans have a very high specific heat. What that means is that they don't warm up much during the summertime, they don't cool down much during the wintertime. As a result, the temperatures over the ocean are relatively moderate. They don't change much from season to season. Another important thing about this, though, is that oceans and areas over oceans don't usually get very hot or very cold. As a result, they're very moderate. That's the reason why I use the word warm for maritime tropical air mass, because warm doesn't really define extreme heat. A warm air mass isn't going to be 110, 120 degrees Fahrenheit. A warm air mass is going to be something more in the 70s and 80s, maybe low 90s, but not really more than that. Whereas when we talk about hot air masses are air masses that can easily be in the hundreds, 110, 120, extremely hot air masses. And so that's why I use the word warm to describe maritime tropical air masses and hot to describe continental tropical air masses. Now the same is true for polar air masses. I use cool for maritime polar air masses because ocean water doesn't get very cold. As a result, the air over the ocean doesn't get very cold. And therefore, I use the definition cool because the air that forms over the ocean really doesn't get much colder than the ocean itself. Therefore, these maritime regions, or these maritime air masses, don't really get very cold. They may go down into the 40s and 30s, but seldomly are they going to get colder than that. Why? Because the ocean beneath them doesn't get any colder than that. And then for continental polar air masses, land can get very cold in the wintertime. And I'm talking temperatures of 20, 10, 0, minus 10, and so on. And that's why I use the word cold there as opposed to cool. The other reason why I want to stress this whole thing, though, is because water temperatures and therefore maritime air masses are more moderate, you can't really get an Arctic maritime air mass or a maritime Arctic air mass. Ocean temperatures just don't get that cold. If they do get that cold, the water freezes and ice forms, and then ice acts just like land anyway. So when we talk about continental Arctic air masses, we're talking about air masses that form over land because the land can get very, very, very cold. Ocean can't. So as a result, there's no such thing as a maritime Arctic air mass. Let me say that again. There's no such thing as a maritime Arctic air mass. But all told, these are our 5 air masses: maritime tropical, continental tropical, maritime polar, continental polar, and continental Arctic. And on a map, they look something like this. Maritime tropical air masses form over the tropical oceans. Continental tropical air masses form over the tropical land areas. And we'll talk about the summer only in a moment. Maritime polar air masses form over the polar oceans. Continental polar forms over high latitude land. Continental Arctic, these form right near the North and South poles. Now, the summer only thing here, this is important to note simply because this particular air mass here in America only forms during the summertime. Now, we don't really need to worry too much about that for this class, so don't stress about it too much. But it's just an interesting fact that you might want to keep in the back of your head, that this continental tropical air mass only forms during the summertime. And the reason why is because the land here can get pretty cold during the wintertime, and that's just because there's a lot of cold air from the north that moves down, and it prevents this continental tropical air mass from forming. One other interesting thing I should note is the United States is not a good source region for air masses. And the reason why is because we're too far north for tropical air masses to form. We're too far south for polar and Arctic air masses to form. As a result, at least the continental 48, so that's the United States excluding Alaska and Hawaii, the continental 48 is not a good source region for air masses. However, once an air mass forms, it travels over the United States. And in fact, polar air masses usually travel to the south. Tropical air masses usually travel to the north. And so these air masses actually interact with one another over the United States. So even though the United States isn't a good source region, it is a good battleground. And that's why the United States has such diverse and interesting weather. It's because we're in the right place. We're in the mid-latitudes. We'll talk more about what that means in the next few lectures. Now, with that said, let me talk a little bit about each of these air masses and some of the implications that they have. One implication is, along a boundary between two of these air masses, you can get a lot of what's called entrainment. Basically, the air from one air mass sucks into the air from the other, or at least sucks along the boundary, sucks into the boundary between the other air mass, and that can create some pretty interesting weather. One of the funnest examples that we get here in California is what's called the Pineapple Express. What happens here is warm, moist air from Hawaii travels north and west along an air mass boundary over to California, where it ends up condensing, cooling, and giving lots of rain. We actually experience these kind of events a few times a year here in Northern California, but every so often Southern California will get hit by one. In fact, there was one I experienced. It was my first year of graduate school, and I was traveling home. I'm from Long Beach, California, and as I was traveling home, I experienced roughly 4 straight days of just rain, not ending rain. And it occurred because of one of these Pineapple Expresses. A warm, moist air mass traveled up along this cold front and gave Southern California several days of just relentless rain. Long Beach, in this time period from December 18th to the 22nd, received over 10 inches in just a 5-day period. The average annual rainfall in the same location is just about 15 inches. So we got 2/3 of our rain in one storm. That's insane. One other interesting air mass that I'll talk about, or one other interesting instance where an air mass got involved that I'll talk about, was in 2014 and 2015. Now, if you actually look back at those years here in California, we were warm and dry during those years. However, on the east coast of the United States, it was extremely cold. Basically what happened was a large chunk of continental Arctic air traveled down into the east coast of the United States. And this created extremely low temperatures, such as a low of -16 on January 6, 2014, a high of balmy, sultry, sweaty 8 degrees on January 7th, 2015, and a few weeks later, a high of 7 degrees on February 19th, 2015. These are substantially below average temperatures. And what allowed this to happen was a huge trough, which in the last lecture we talked a little bit about the jet stream. A huge trough is when the jet stream dips to the south, and this allowed this continental Arctic air mass to pour into the eastern United States. And it looked something like this. Now, people confuse this for something called the polar vortex. And the polar vortex is basically this large, high-pressure area that's present over the North Pole. And when this trough forms, this high pressure is able to extend further south. Now, this did happen. However, the polar vortex was still pretty present over the North Pole. It just expanded further south. That's all I'm going to say about that. This was an image taken in January of 2014 from a gentleman named Hank Kane who was landing in Chicago. And if you've ever seen The Day After Tomorrow, and that storm comes through and then they show after the storm comes through, and it just looks very frigid. When I saw this image, that's what I thought of. You can see much of the lake is frozen, much of the city's covered in snow, the way the sun is reflecting off the ice. It's a beautiful image, but it just shows you how cold Chicago was during this time. And this happened again because this large Arctic air mass with the polar vortex as its center stretched outward and traveled down into the Midwest and the East Coast. Now, that's it for air masses. Next time we're going to talk about what happens when air masses bump against each other. Those are called fronts, and those are where really the interesting weather takes place. Until then, I'm Terrence Mullins.